Hello, everybody. Now we are going to see how we can deal with Cauchy's equation that we derived last video. So if we look at this equation, you would see that we have three velocities. So these are the variables that we want to calculate from this equation. We have three variables. We have 9 components of the stress sensor. We have the and the pressure. Okay, so we have the pressure, the shear stresses, the three velocities. So we have a lot of variables that we have here in this equation that we want to calculate. And I mean the density, it's not the pressure. The pressure is already in the stress sensor. So we have the density, the three velocities, and 9 stress sensors. 3 of them are dependent. So we have the independent variable are 6, 3, 1. There are 10 independent variables, and we have only 4 equations: the 3 components of Cauchy's equation and the continuity equation. So by just the simple logic, these equations are not enough, or the information that we have are not enough to solve these equations. We need more information because the number of equations must be equal to the number of unknowns. And the equations, I mean the information that we need to know have to do with the type of fluid. Because if you think of this, we said that the sigma ij, which is the stress tensor, contains the shear stresses, and the shear stress is 100% dependent on the type of fluid. It's going to be different in case of Newtonian fluid than non-Newtonian fluid, from shear thinning to shear thickening to Bingham fluid. So even without having this point of having the equations and unknowns, there is no way we can solve this equation without knowledge of how the fluid behaves. This is a very, very, very logical thing. You need to know how the fluid behaves so that you can know how to calculate its shear stresses. Okay, so with these 6 information, if we know these 6 shear stresses, we can now have number of equations equal to the number of unknowns, and we'll have a good understanding of how the fluid behaves, and we can solve the problem, or it's not solve. We can have solvable equations. Okay, because there are a lot of equations. You have 10 equations and 10 unknowns, so it's a big deal. And now these equations that we need to know are called constitutive equations, which is the relation between shear force and rate of deformation, which is tau, is the constitutive equation. This is how we call them. And to make things simple for us, we are going to deal with the simplest form of shear stresses, which is the shear stress of Newtonian fluids. So we are going to limit our discussion for the coming slides, or the rest of this chapter, to Newtonian fluids only, because they are the most easy one to model, which is not easily modeled, but they're the most easy to model. Okay, so from now on we are going to only deal with a special case of Cauchy's equation, which is Cauchy equation in case of Newtonian fluids. And also to make it more easy to deal with, it's going to be only for incompressible fluids, for isothermal flow. And we limit it for incompressible fluids and isothermal flow because this is what is going to make the equation more easy to deal with. Incompressible is understood, Newtonian is understood, but isothermal flow, meaning that the temperature is constant. And we care about the temperature here because the viscosity is very, very dependent on the temperature. So if there is change in temperature, then the viscosity will vary, and then the derivation that we are going to do is not going to be valid. So it has to be clear that the derivation, and again, this is one of the goals of having or going through this derivation, is to know why we are going to have these limitations on the final equation. Because without these conditions, the equation is not going to be valid, and this is what we base our derivation on. So for the constant viscosity, tau is going to be We know in case Newtonian fluid tau equals mu times du by dy. But in the previous cases, like chapter 2, when we went through this equation, we had only velocity in one direction. Okay, when we had the two parallel plates and the fluid was flowing between the two parallel plates, the one is sliding upward and the bottom is stationary. We said it's du because the fluid was in one direction, and dy because this is the distance where the velocity is changing with. So it was very, very straightforward. Now we have a different story because we have three components of velocity. And we have three different coordinates. We have velocity x changes with x, velocity x changes with y, velocity x changes with z, the same for y changing with x, changing with y, changing with z, and the same for z changing with x, y, and z. So we have a lot of different alternatives. So the shape, and without going into details why it looks like this is how the shear stress looks like. In the shear stress tensor looks like. So it's 2 times mu times epsilon ij, where epsilon ij, it's the rate of deformation, which is du, corresponds to du by dy before. So all of them are du by dy by dx, y, or z, but they are in different coordinates. Anyway, so to make this long story short, what I want to get here is now we have an expression for tau ij. Okay, or this tau xx, tau xy, tau xz, which was an issue that we faced in the previous slide, which is this. We couldn't find a way to know this. Now with the assumptions that we make, we have a form for this equation that we can apply to the equation. And now you can see here in this equation, if you know the viscosity, we have here, instead of having different taus, we have velocities. So it's the same variable that we had in the beginning. And if you see here, we had three velocity components. Now all the variables here are the velocity components. So we are replacing the sigma ij, which is something that we didn't know, with velocities. So we are reducing the number of variables by 6. Okay, and now this is sigma ij is going to be the normal stress plus the shear stress, and now by putting everything together, we will reach an equation that's a very, very famous equation, which is called Navier Stokes equation. And Navier Stokes equation is a special case of Cauchy's equation in case of Newtonian fluid, incompressible flow with constant properties, or at constant temperature. So just to make this long story short, this is the shape of Navier Stokes equation. We have here the total derivative times rho equals dp by dx, negative dp by dx plus rho gx plus mu times the del 2 ux. This is an x component, y component, and z component, and it can be written as one equation like this. So again, it's very important, it's very, very important to remember that Navier Stokes equation is only valid for Newtonian fluids. It can work for steady and unsteady flow. It has to be incompressible flow and isothermal flow. And now we have only the velocities, the pressure, and the density and the gravity are the only parameters we have, instead of having much more variables before. And now we can have a look at the expanded form of the equation, and this is what we are going to use for the rest of this chapter. We have the incompressible continuity equation, and we use the incompressible continuity equation because these are all for incompressible flow. We have to make it consistent. The equations must be consistent for all of them. So this is a continuity equation, x, y, and z components of Navier Stokes equation. Okay, for just a note here, I put ux, uy, and uz to make it easy for you to understand what is the velocity. In the textbook, it's using u, nu, and w for ux, uy, and uz. So I think what I have here is more easy to understand, at least for me. And these are the equations in case of cylindrical coordinates. So when we solve problems, we are going to start from here, whether these equations or the next ones. We don't have to start from the very beginning, from the equations before the derivation. We're going to start from here. But even though this is something that looks scary to many people, how can we solve problems that are like this? They're all partial differential equations in 4 parameters, x, y, z, and t. And they're 4 coupled equations. We cannot solve each one of them away from the others. So how can we deal with these equations? So this is going to be the topic that we are going to discuss in the next video, inshallah. So I'll see you then. Goodbye.